Hey, so this is looking at how we can put a number to the ions that are dissociated. So the question here is, how do we determine the quantitative aspects of dissociation? So when a chemical dissociates into solution, can we put a number? Can we calculate how many, what the concentration of the ions are? Yeah, we can. So when we do that, we're actually looking at the ratio of the ions dissociated comparing to the initial. When we're looking at the ratio, we're actually looking with a constant. So what that means is that this, looking at the ratio of the ions associated, there's an expression called the equilibrium law expression. This expression highlights what happens when you compare the ratio of the product, which are the dissociated ions, to the initial. So this is the general expression formula. You can see that you have K, which is an equilibrium constant. This K is constant, so it actually does not have any units. And you have your concentration of ions here. This top part in the numerator of this is your products. And then this is all divided by the reactants, which is your HCl. So you can see that this is your products here at the top. And then this is dividing by the reactants, which gives you a ratio. So products over reactants. So then when you calculate this, you can sort of guess what happens to your constant K, right? If your K is a really, really big number, how did you get a big number from this ratio? Well, you can see that in order to get a big number, your products must be a really, really large number, right? That means that if your products is a large number, the amount of products, the ions that you dissociated in your reaction must be really big. That means that you actually have a big amount of dissociation, a lot of dissociation. So then that will give you a large K. You know, another scenario where K is very small, if this is a small number, that means that your denominator has to be really, really big, or your numerator is really small. That means that you don't get that much dissociation. That means that in your equilibrium, when this goes into reaction, you actually don't get that much dissociation if your K is a small number. So why are we talking all of this? Well, let's look at water, for example. Remember, water can be ionized into two forms. So you have your hydronium ion. So this is your H3O+. How do we get your hydronium ion? Well, remember, based on Bronson and Lowry's definition, an acid is a proton donor. So if this water acts as an acid, it donates one of these protons to it. So this will give you your hydroxide ion, one less proton, and whereas the other one will gain a proton, gives you an H3O plus, which is your hydronium ion. Or if you were to look at the proton, how we get this H plus, this H2O can be dissociated into H plus or OH minus. Okay, so there is actually a constant to look at water, because water, if we were to look at the equilibrium law expression, this would really just be H plus, which are my products, times the concentration of hydroxide. And then we're not going to divide by anything, because liquids, like states such as liquids or solids, don't get used in this equilibrium law expression, because the concentration of the liquids and solids actually doesn't change, right? So that you only use the aqueous forms. That's the only ones that gets included. So if we were to look at this, here's my Kw for your hydronium, here's my Kw for your proton, and the Kw constant is this. So this is a constant number that is always going to be present. This is at your room temperature. So what does this number represent? What is this telling you? Well, you can see that it is a very small number. It's times 10 to the negative 14. So very, very small. Does that mean that you're going to have lots of products or ions dissociated? No, because of this small number. That means that when you put water into solution, like the water here into solution, majority of the form that's still in your solution is still your H2O liquid and not the ionic form. That means that if you were to have a beaker of water, what it's telling you is that you actually have a lot of your H2O liquid still, and not so much of the ions. Okay, so that's what your Kw is. So what does this number represent? It means that when the concentration of H plus and hydroxyl ions are multiplied, you get a very small number. So that means that water actually doesn't dissociate that well into its ions. Oh, I don't know why I wrote this part here. So that really tells you that people tell you that water conducts electricity. Pure water actually doesn't. It's the salts that's dissolved into water that conducts the electricity. So those are the ions that carry the electrons. Alright, so that's your introduction of your equilibrium law expression, looking at your Kw, which is the expression for water, and what this K, the constant, represents. And in the next video, we're going to look at some calculations involving this water constant and how this actually can eventually be used to calculate your pH. So hopefully that video has helped you. Thanks for watching.